I'll go straight into it, if this works.
Sorry, it's okay for you to say next slide.
Okay, yeah, so next slide.
But you have a power laser pointer.
Oh, yeah, laser pointer. Okay, so next slide.
Yeah.
First slide. Okay, I will not give an introduction to CALPHAD. I expect people know that. I will also not give an introduction to the Scheil equation, which I'll be talking quite a lot about. So I also expect people to know about that. And I'll jump right into the controlling factors for additive manufacturing. And the one I'll be talking about most is the chemical controlling factor. So equilibrium thermodynamics, phase diagrams, but also Scheil simulations that do in fact predict chemical segregation, chemical homogeneities during the process. Apart from that, there are also physical aspects that control microstructure. These are to do with the solidification rates, thermal gradients, and they then determine the microstructure. I'll talk a very small bit about this, but the main thing. Oh, now it works. Okay. Oh, gotcha. Okay. And so these are the things that can be calculated using CALPHAD. Okay, so I'll just show one slide on what a Scheil curve looks like. What you get from a Scheil curve, you get temperature in function of mole fraction solid in function of temperature. And basically that just shows you how, as you cool down, you get a higher and higher fraction of solid until you get the final solidification down here, and that's basically the solidification range. The other thing you can calculate is in function of fraction solid. You can also calculate the composition of all the phases. And this is then typically interpreted as segregation on a small length scale. So in conventional casting, that is interpreted as segregation between the dendrites. In additive manufacturing, where you might have tiny cells growing, it's the segregation between the growing cells. Okay, so that's what you got, basically. Now, a slide I like to show is that the Scheil curve will also give you an immediate information on the microstructure you're getting. So we typically color these sections of the curves in different colors. So in the first section of this of the Scheil curve, you've got liquid plus FCC. So this is an aluminium alloy, cast aluminium. So you've got primary FCC aluminium precipitating, and this would be this red zone here, which are the growing dendrites. And then the color changes to green. And if you look at green, you've got, well, diamond, which is silicon. It's the diamond structure, but it's in fact effectively silicon, plus FCC. And what happens here is basically, if you think of the liquidus projection of the phase diagram, you're hitting a liquidus trough, and then you start following the liquidus trough, so you've got a co-precipitation of silicon plus aluminium. And this is then this green area, which is in this case eutectic type microstructure, and then you come to the very end, this purple curve here, part of the curve where you get then intermetallics precipitating. So the Scheil curve directly will give you some information on the microstructure. Okay, now going to the assumptions we make, the classic assumption in Scheil, in the Scheil equation. The first is that diffusion in the liquid is infinitely fast. Now for additive, this is probably quite true because you've got quite a moved melt pool. There's quite a lot of motion going on there, so that's probably a true assumption. Then you've got the diffusion in the solid is negligible or zero. This is the classic Scheil assumption. So that basically the composition you get at the solidification interface, that's frozen in afterwards. And the third important assumption you make is that you have equilibrium at the solid liquid interface. This means you have enough time for basically for partitioning of the elements from the liquid and the solid. So equilibrium, thermodynamic equilibrium at the solidification interface. These are the classic assumptions. Now, what processes do these classic assumptions, or which processes are they suitable for? This is casting, arc welding, laser welding. So basically processes with moderate to fast cooling. In these types of process, the classic Scheil assumptions hold relatively true. And concerning the materials, it's not true for all materials, so you need to have relatively slow diffusion in the materials in the solid. And now we've made a bunch of modifications to the Scheil equation, and the first one is that we consider back diffusion in the solid. So we say that diffusion in the solid is not negligible, and we have two versions of that. The simpler one that's been around for a long time is that diffusion in the solid is infinitely fast for certain elements. And the second one is that we actually quantitatively account, because we have the Dictra module and we have mobility databases, so we can quantitatively calculate diffusion in the solid phase. And this modification of the Scheil equation then basically expands the materials where it's applicable to materials that have fast diffusion in the solid phase. A very typical one is steels, where you have carbon, for example, and that's well known that during normal casting or even additive manufacturing, there is basically enough time for carbon to diffuse in the solid, because it simply diffuses so fast. Now, the next modification we've made is, and this is this third assumption here, that we have equilibrium at the solidification interface. Now, this assumption breaks down for additive manufacturing when you have a rapid motion of the solidification front. And this is the solute trapping model that we've relatively recently introduced. And this is used in the case where the solidification interface is so fast that there's not enough time for partitioning of the elements between the liquid and the solid. So basically the solidification interface grows over the liquid phase and incorporates solutes directly in the solid. Okay, and now here, this is really fast solidification rate, can be additive or splat cooling, melt spinning, and so on. And I think this is a valuable extension to additive manufacturing where this is often the case. Okay, a very quick recap. So this is what we got: classic Scheil with fast diffusion, for example, for steels, Scheil with calculated back diffusion. Basically, can be for all sorts of elements where we expect to have fast diffusion in the solid or fast enough diffusion in the solid. And finally, Scheil with solute trapping. But which of these various flavors of Scheil should you use? And here I've just made some examples for example, nickel, 30 chromium, 5 niobium. So these are all very, very slow diffusing elements, no interstitials. And the dotted line is the equilibrium. And then we have Scheil, classic Scheil, and Scheil with back diffusion. And there's virtually no difference, right? So here, the diffusion of these elements is simply so slow that nothing happens in the solid, and you can just use classic Scheil. But if you change that to steel with carbon, then if you do a classic Scheil, you get this ridiculous depression of the solidus temperature, which is known to be untrue. And so what's been used for a long time for steels is Scheil with carbon as a back diffuser. So carbon is just assumed to diffuse infinitely fast, and then you get this solidification curve, which is quite reasonable. And then let's look at another one, aluminium 5 magnesium. Now the point here is that magnesium is actually quite a fast diffuser in aluminium alloys. And there, even with relatively moderate cooling rates, you rather quickly end up more or less halfway between classic Scheil, which assumes no back diffusion, and equilibrium. And I was happy to hear in a talk this morning that experimentally they say, yeah, we're somewhere half between equilibrium and Scheil. But yes, so please calculate the back diffusion, and probably you'd be able to get exactly the curve you're looking for. And now the new one, which is solute trapping. This is for aluminium with 5 copper. And this solute trapping, and I'll be talking, people probably don't know that, too well. I'll give some details in just a minute. That actually also depresses the liquidus temperature, right? So it reduces the liquidus temperature, and in effect, what it does is it depresses the liquidus temperature and also increases the solidus temperature to the T0 line. So where the Gibbs energy of the liquid and the solid are identical, that's the T0 line, and that's basically the limit of solute trapping at very fast velocities of the liquid-solid interface. Okay, good. So I should be about halfway through, and that just a short overview of the different flavors of the Scheil equation that we have implemented. And I'll go through some examples. They're more or less randomly picked from literature, and just shine a little bit of a spotlight on them, and just to see what's what's going on there. And the first one, actually, I didn't realize this, but this is a paper, a Nature paper with Professor Jägle as co-author. I didn't realize this until I actually made this slide, so that's a funny coincidence. So what did they look at? They had two different versions of Inconel 738, and it's known that this one here with 0.11 silicon is not printable, and you need to decrease the silicon content here to low values to make it printable. And the question was why. And this is copied directly out of the paper. So it's not my work at all. I don't want to take any credit for this. So this is just taken out of the paper. But here you see this is a slice of the built sample cut. What's that? Build direction perpendicular to the build direction. So I think here you see the cells sort of pointing out towards you, and you see this segregation around the cells, and you also see everything happens at a very small length scale. And yeah, they had access to very nice experimental equipment, atom probe tomography. Not everybody has this, and they were able to measure the segregation between these growing cells or dendrites. And in a nutshell, what they found out was that if you have silicon in the sample, then you have positive segregation of silicon here, but that doesn't seem to be the cause. The cause seems to be that together with that, you have segregation of boron and carbon here. And with the low silicon here, you don't have that. So everything else looks more or less similar, but you don't have this segregation of boron and carbon. And what they did then is they took these compositions and just calculated the solidus temperatures. And this is what they get here. And they find, obviously, or what they find is a strong dip in the solidus temperature because of this segregation of these two elements. And that is then what causes the hot crack problem for the sample with higher silicon content. And the paper goes on to discuss why silicon affects boron and so on, has to do with interactions and so on, chemical interactions between the two. But my thought was, wouldn't it be nice if I could just calculate these segregation profiles and we wouldn't need atom probe tomography to get this? And I just did a classic Scheil calculation, took the data out of the plots they showed, and the results were quite disheartening, actually. So, for example, cobalt here, Scheil predicts quite a negative segregation. They see relatively little. Titanium is predicted to segregate very strongly. And boron is an interesting one here. There, I see the prediction is there is absolutely no boron in the FCC phase. So is this the best we can do? Because this wouldn't be too good. And the answer is, of course, part of the answer is to consider solute trapping, because solute trapping will change that quite significantly. And first, just an answer to this, because this looks funny. So where is the boron? If it's not in the FCC phase, it must be somewhere. Well, it just stays in the liquid. So this is one of these cases where the boron is pumped out of the solid. It just doesn't go into the solid at all, and it just ends up at the final solidification point, and then maybe forms into metallic phases or some other case. So it doesn't go into the solid at all. But if you switch on solute trapping, you change the segregation profiles quite dramatically, and for some, you can, depending on the scanning velocity that you choose, you can get quite a good representation of, for example, cobalt segregation here. The aluminium segregation changes from negative here in the classic shile to positive if you have quite a fast scanning rate. So it makes quite a dramatic change to the segregation profiles. And for me, this is quite promising. And one of the things that you do see once you switch on solute trapping is that you do get boron in the FCC phase. Okay, and this is solute trapping, so it's basically the FCC phase traps the boron. And you'll also see that there are certain elements react strongly or have a strong, solute trapping has a strong influence in certain elements and others not. And for that, we have to dive into very slightly into the equations behind solute trapping. And basically what the solute trapping model does, it modifies the K here, the partitioning coefficient in the Scheil equation modifies K. And what goes into the solute trapping is delta, which is the thickness of the interface, the velocity, which is user input, so how fast the solidification interface is traveling, and the diffusivity. Okay, so various elements have a different diffusivity through the solid-liquid interface. The solid-liquid interface is assumed not to be sharp, it's a diffuse interface, and there's a diffusion through that interface. And various elements will have different mobilities through the solidification interface. So, for example, boron is small, it's fast diffusion, it will move through that interface very quickly, and that's why you get quite a strong effect for boron. Okay, next one. I've got three more examples. I think I'm just about in time. Okay, one is if you want to move from a conventional manufacturing to additive, you see unexpected things. And a famous one here is delta precipitation in an Inconel alloy. And this paper is from Lindvall, Greta Lindvall. And what did she do? And this again, just showing how thermocalc tools can be used to look at a problem like that. So first you calculate the segregation profiles, here Dictra was used, and then what you do is you take the composition profiles and do precipitation simulations at different positions in that on that segregation profile, and to see which phases precipitate. And you see you get a double prime. So if you have a highly segregated area, you get heavy formation of gamma double prime, which is the precipitate you want. That's then very quickly replaced by delta. Okay, and at the one where you have less segregation, you're already like, you can't avoid having delta and gamma double prime depending on where you are in the composition range, right? They cross these two curves. So if you want a good amount of gamma double prime in the unsegregated area, you need to do a heat treatment where you've already got delta phase in the segregated area. So obviously this means that you have to do a homogenization of this material to prevent that. Okay, and talking about homogenization, this is another application of thermocalc, how to optimize your homogenization. This is for Haynes 282. So again, nickel superalloy with a lot of heavily alloyed nickel superalloy, and you get a very strong segregation here. And you need to homogenize that. And then the question is here, what are the optimal homogenization temperature? This is again a useful application of a Scheil curve. So you know that you have to be below this this final solidification, which is significantly below the equilibrium solidification temperature. So you know you have to be below this because you don't want to melt your material, right? So that's the first sort of use of this Scheil curve. But then what will happen is diffusion will start, and this final solidification, as all these segregation here is removed by diffusion, this final solidification temperature, the solidus temperature, will increase. So you could increase your homogenization temperature during the process. And this is what was done. And you can do that calculation directly in the diffusion module. And you can see that if you just use a rather silly homogenization temperature of 1100 degrees, you need, even after 22 hours, you've still got a significant amount of segregation left. But if you do a two-step, so start at 1100 until the final or the solidus temperature is increased enough to increase your temperature to 1200, then you can reduce the homogenization time to 11 hours. Again, this is a Jablonski paper from them. And the final example, we started a bit late. Okay. Okay, I'll just go through this very, very quickly. So this is again, a very nice application. So what you're doing here is you're getting CALPHAD data to go into the thermal as input to FEN model, for example, and then you can use the output of a FEN model for precipitation and growth simulations. And this was this example here, and where exactly this was done. So if you do the FEN model, then you get this temperature in function of time, and then you can use that temperature as input to precipitation calculations, and then finally get mechanical properties. So these are the sort of things that are going on, and these are sort of things that you can use. Thermocal plus the models we have for additive manufacturing. I'm sorry, well, I don't think it was too bad. Okay, that's it. Thank you.